shrinking. 128 was barely our galaxy, along with thousands of others, is being pulled at 600 kilometers per second towards something we couldn't directly observe for decades, because our own galaxy was blocking the view.
Subscribe if you want more of the cosmos. This is White Space, settling. There is a moment, somewhere around 500 BCE, when a Greek sailor watches a ship disappear over the horizon. The hull vanishes first, then the mast, the flag last of all. This sequence, that precise orderly sinking, troubled certain minds for generations. If the Earth were flat, a ship would simply grow smaller until it became invisible. It would not sink. It would not vanish from the bottom upward. That observation, small, almost mundane, was the crack through which an entire new understanding of the world eventually poured. We live on a sphere. We figured that out by watching a wooden boat. Now we face a larger question, not the shape of the ground beneath our feet, but the shape of everything, the shape of space itself, of the universe as a whole, from one edge, if there is an edge, to the other. This is not a question you can answer by watching a ship, but it is a question we are trying to answer slowly with instruments far stranger than eyes. The difficulty begins immediately. When we talk about the shape of the Earth, we mean something we can, in principle, circumnavigate. We can fly over it. We can photograph it from orbit. The universe offers no such vantage point. We are inside it. There is no outside from which to look. Everything we know about its shape must be inferred from light and mathematics and the behavior of space itself, and from a faint afterglow that still fills every direction of the sky, the relic radiation left behind by the first moments after the Big Bang. What cosmologists have found is this: the universe appears at the largest measurable scales to be flat. Not flat in the everyday sense of a table or a floor, but flat in the precise geometric sense. Flat the way Euclidean space is flat, where parallel lines never converge and never diverge, where the interior angles of a triangle always sum to exactly 180 degrees. This flatness is not a certainty. It is a measurement. And every measurement has a margin of error. But within that margin, space is not detectably curved. Three broad geometries are possible. In the first, space curves positively, folding back on itself like the surface of a sphere. But in dimensions we cannot visualize. In such a universe you could set out in one direction and eventually return to where you began, the way a traveler circling the globe returns to their starting city. Two straight lines sent out in parallel would eventually meet the way lines of longitude meet at the poles. A universe of this type would be finite, bounded, but its boundary would not be a wall. It would be a seam, an invisible closure. The total energy content of such a universe would have to be high enough to curve space closed. In the second geometry, space curves negatively, opening outward like the flare of a saddle or the throat of a horn. Parallel lines diverge. The universe in this case extends forever, and 2 points moving apart from each other continue moving apart faster and faster without limit. Energy here is low. Expansion accelerates without end. And in the third case, the case measurements currently favor space is flat. Parallel lines stay parallel. The expansion of the universe neither collapses back upon itself nor accelerates into infinite emptiness at a runaway rate. It proceeds. The total energy density of a flat universe sits at what cosmologists call the critical density, a precise and delicate balance. But flatness alone does not determine shape. A cylinder is flat in the geometric sense, and yet is clearly not infinite. A torus, the three-dimensional equivalent of a donut, can be geometrically flat while still being finite and topologically complex. The universe might be flat in curvature and still fold back on itself in ways that mean a traveler heading in one direction would eventually return from the opposite direction.
Some researchers have pointed to anomalously large features in the cosmic microwave background, oversized warm and cold patches, as possible signatures of just such a topology.
The universe as a shape is not yet settled. What we know is that on the scales we can measure, space does not visibly bend. Before space could have a shape, it had to exist. And according to the best current understanding, it came into existence approximately 13.8 billion years ago, along with time itself. Before the Big Bang, a phrase that already strains language. Since there was no before, all the matter and energy that would become stars, planets, galaxies, and everything in between was compressed into a state of such extreme density that the physics we use to describe everyday reality breaks down entirely. There was no space in which to be, no time in which to wait. And then, for reasons that remain genuinely unknown, that state changed. What followed was not an explosion in the ordinary sense, matter flying outward through pre-existing space. Space itself expanded. The distance between every point in the universe grew. It continues to grow now. And the light emitted in those first moments scattered and scattered and scattered across the expanding fabric of space for nearly 380,000 years until the universe cooled enough to become transparent, has been traveling ever since. We detect it today as a nearly uniform glow of microwave radiation in every direction. It is the oldest thing we can see, and in its faint temperature variations, ripples of 1 part in 100,000 is encoded the entire future structure of the cosmos. One of those temperature variations has attracted particular attention over the past 2 decades. It is called the cold spot. Located in the constellation Eridanus, roughly 3 billion light-years from Earth. It is a region of the cosmic microwave background that is measurably colder than the surrounding sky, about 70 microkelvin below the mean. That number sounds trivial. It is not typical temperature fluctuations in the background radiation average around 18 microkelvin. The cold spot is nearly 4 times larger than expected. And it occupies a region of sky corresponding to a volume of space nearly 2 billion light-years across. When astronomers examined that volume, they found something extraordinary. Almost nothing. No galaxies in the numbers that should be there. No dense clusters, no bright concentrations of matter. What they found was a supervoid, a region of space, so depleted of ordinary matter that it strains the predictions of standard cosmological models. An ordinary void between galaxy clusters might span a few 100 million light-years. The Eridanus supervoid is 20 times larger. If the disk of our own Milky Way galaxy, 100,000 light-years across, were a coin, you could stack 20,000 of those coins side by side and still not bridge the width of this void. The question is what made it. Several explanations have been proposed and none is fully satisfying. One hypothesis invokes the integrated Sachs-Wolf effect. As photons from the early universe travel through a large void, they gain energy falling into the void's gravitational potential well, then lose energy climbing out. If dark energy causes the void to expand during that transit, the photons emerge slightly colder than they entered. This would explain a cold spot, but the calculations suggest the known Eridanus structure is too large and too cold to account for the full anomaly on its own. A more exotic proposal holds that the cold spot might be the imprint of a collision or quantum entanglement between our universe and a neighboring one during the period of cosmic inflation, the extraordinarily rapid expansion that preceded the hot Big Bang phase. Under this view, what we are seeing is a scar left by contact with another branch of reality, another bubble in a vast multiverse of separate spacetimes. This idea is speculative in the extreme, and most physicists treat it with appropriate skepticism, but it has not been ruled out. What the cold spot has done, beyond inspiring theories, is force a re-examination of what the large-scale universe should look like. Standard cosmological models predict a universe that is, on scales above a few 100 million light-years, statistically uniform.
No region should be dramatically emptier or denser than average. The Eridanus supervoid challenges that prediction. Its existence does not disprove the standard model, but it sits at the edge of what the model comfortably allows.
Whether it represents a statistical fluke, a gap in our physical understanding, or something genuinely new remains an open question. One that improved surveys of the cosmic microwave background and the three-dimensional distribution of matter may eventually resolve. There is another mystery at the opposite extreme of scale. Not a vast emptiness, but an object of almost incomprehensible compactness and mass sitting at the center of our own galaxy. Sagittarius A star is the name we give to the radio source at the Milky Way's heart. Decades of observation have established that it is a supermassive black hole with a mass of approximately 4 million times that of our Sun, compressed into a region no larger than the distance from the Sun to Uranus. It is invisible in the direct sense light that crosses its event horizon does not return. But the stars orbiting it trace tight ellipses at speeds of thousands of kilometers per second, paths that can only be explained by the gravitational influence of an enormous mass in an extraordinarily small space. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star itself, not the black hole, but the glowing ring of hot plasma swirling around it. What surrounds this object is a dense fog of gas and dust that blocks visible light entirely. Only radio waves, infrared radiation, and X-rays can penetrate, and in those wavelengths, astronomers have found something strange near the black hole, a thin, curved thread of material stretched across several light years of space, apparently pointing towards Sagittarius A star like an accusatory finger. Such structures, magnetized filaments near the galactic center, are not new. Several hundred of them have been catalogued over the years, oriented roughly perpendicular to the plane of the galaxy. But this particular filament is different. It curves, it points directly toward the black hole, and it is far closer to Sagittarius A star than any previously known filament within about 2 light years by current estimates, with the filament itself stretching roughly 3 light years in total length. 4 hypotheses have been advanced. The filament might be a coincidental alignment, an object that appears connected to the black hole only because of our viewing angle, the way a distant mountain can appear to balance on a fingertip. It might be composed of high-energy particles accelerated by the black hole's accretion disk and its powerful magnetic field, similar to the plasma jets that emerge from far more active galactic nuclei. It might represent a cosmic string, a one-dimensional topological defect left over from the earliest moments of the universe, now falling toward the black hole and distorting as it approaches. Or it might genuinely be threading through the event horizon, giving us an indirect view of what lies just inside. That last possibility invites a detour into some of the strangest physics anywhere in theoretical astrophysics. Beyond the event horizon of any black hole, the surface from which nothing escapes, some solutions to Einstein's field equations predict the existence of a second surface, deeper inside, the Cauchy horizon. At the event horizon, the escape velocity equals the speed of light. At the Cauchy horizon, something more radical happens. The mathematics of space-time change character. The dimension we normally experience as time becomes space-like. All moments, past, present, future, collapse toward a single point of infinite density. An observer who crossed the Cauchy horizon would, in theory, encounter the entire future history of the external universe compressed into a finite moment of experience. Whether such an observer could survive, or whether quantum effects destroy the Cauchy horizon before it can be reached, is unresolved. What is certain is this: the physics we use to describe the universe breaks down at singularities, and black holes contain singularities.
The threat of material near Sagittarius A star will not deliver us answers about the interior of black holes directly, but it has reminded astronomers once again that the center of our own galaxy remains one of the most extreme and least understood environments in the known cosmos. There is a direction on the sky, somewhere in the broad region around the constellations Centaurus and Hydra, toward which our galaxy, along with thousands of other galaxies, appears to be flowing. The flow is not dramatic on human timescales, but it is real. The local group, the collection of galaxies that includes the Milky Way and the Andromeda galaxy and several dozen smaller satellites, moves at roughly 600 kilometers per second relative to the cosmic microwave background. Some of that motion is explained by local gravitational attractions. Much of it points toward a region that astronomers once called simply the Great Attractor. For decades, the Great Attractor was a frustrating puzzle because it lies almost directly behind the densest part of the Milky Way's disk, the band of stars and dust that defines our galaxy's plane on the sky. This region, where our own galaxy's gas and dust absorb and scatter most optical light, is called the zone of avoidance. Galaxies behind it are hidden not because they do not exist, but because we cannot see them in visible light. The zone of avoidance is not a physical barrier, it is an observational one. When radio telescopes, X-ray observatories and infrared surveys finally pierced the dust and catalogued what lay behind it, astronomers expected to find something massive enough to gravitationally accelerate not just the local group but hundreds of thousands of neighboring galaxies. What they found seemed at first almost disappointing, a cluster of galaxies, significant, but not obviously extraordinary. This concentration, known as the Norma cluster, sits within a larger overdensity, sometimes called the Great Attractor region. But when the influence of just this cluster was calculated, the numbers did not fully account for the observed motion. Something else was pulling. Something larger, farther away, mostly hidden. That something turned out to be the Shapley supercluster, located approximately 650 million light-years from the Milky Way in the direction of the constellation Centaurus. The Shapley supercluster is the most massive concentration of galaxies within a billion light-years of us. Its total mass is estimated at roughly 10 quadrillion solar masses, 10 million billion times the mass of our Sun. It contains dozens of individual galaxy clusters, hundreds of groups, and many thousands of individual galaxies bound together by gravity into a single vast structure. The Great Attractor, immense as it is, turns out to be merely a local feature embedded in the much grander gravitational basin created by Shapley. The implications are unsettling in a productive way. Our galaxy is not drifting randomly through space. It is being pulled and has been pulled for billions of years toward a target we could not even see until recently hidden behind our own galaxy's plane. The Great Attractor contributes perhaps 44% of the local group's peculiar velocity. Much of the rest is attributable to the broader Shapley flow. And what lies beyond Shapley? What larger-scale structures might be exerting their own influence is a question that surveys are only beginning to answer. To appreciate what astronomers mean when they discuss structures like the Shapley supercluster, it helps to understand the full architecture of the universe on the largest scales. Begin at the scale of our own galaxy, a disk roughly 100,000 light-years across, containing several hundred billion stars. The Milky Way is large by most standards, but it is not exceptional. In the local group, it shares space with Andromeda, which is similar in size, and with about 50 smaller companions. The local group itself is small by the standards of galaxy collections. The nearest major cluster, the Virgo cluster, lies about 54 million light-years away and contains at least 1,300 galaxies, possibly several thousand. The Virgo cluster is the gravitational anchor of the Virgo supercluster, a loose association of galaxy groups that spans about 110 million light-years. For most of the 20th century, this was thought to be the largest structure the Milky Way belonged to. in 2014, a new map of galaxy velocities revealed something much more encompassing.
The Virgo supercluster, it turned out, is just one tendril of a far larger structure, the Laniakea supercluster, which extends across some 520 million light years and contains the mass of roughly 100 million billion suns. Laniakea, a Hawaiian word meaning immeasurable heaven, is the river basin in which the Milky Way sits. Its hundreds of thousands of galaxies all drain gravitationally toward a common center of attraction, the same great attractor region we have already discussed. But even Laniakea is not the largest known structure. The universe, on scales above a few hundred million light years, organizes itself into what cosmologists call the cosmic web, an intricate three-dimensional network of filaments, walls, nodes, and voids that fills all of observable space. The filaments are the strands of this web, long, narrow concentrations of galaxies, gas, and dark matter that stretch hundreds of millions of light years across space. At the points where multiple filaments intersect, matter piles up into massive galaxy clusters and superclusters. The densest nodes in the web, where the gravitational well is deepest and the concentration of galaxies is highest. Between the filaments lie voids, vast, nearly empty regions where the density of matter is far below the cosmic average. The walls of the cosmic web are flat or sheet-like concentrations of galaxies, typically thinner than they are wide. The first such wall to be identified was the CFA2 Great Wall, discovered in 1989. It stretches approximately 500 million light-years in length, 300 million light-years in width, and only about 15 million light-years in thickness, a vast, flat slab of galaxies embedded in the fabric of space. Its full extent is partly obscured by the zone of avoidance, so its true dimensions may be somewhat larger. The Sloan Great Wall, identified in 2003 from data collected by the Sloan Digital Sky Survey, is larger still, roughly 1.37 billion light-years from end to end, located about 1.2 billion light-years away. For several years, it held the record as the largest known structure in the universe. Then came the Hercules Corona Borealis Great Wall, detected through the clustering of gamma-ray bursts, the most energetic explosions in the cosmos, produced when the most massive stars collapsed at the ends of their brief lives. The Hercules Corona Borealis Great Wall spans more than 10 billion light-years, accounting for roughly 10% of the diameter of the observable universe. Its existence challenges theoretical models of how structure forms. Standard cosmological theory predicts that, on scales above about 1.2 billion light-years, the universe should be statistically uniform. Nothing larger should coherently exist as a structure. The Hercules Corona Borealis Great Wall is more than 8 times that theoretical limit. It either means the theoretical limit needs revision, the statistical interpretation needs refinement, or both. In 2021, another remarkable structure was announced, the Giant Arc, a crescent-shaped arrangement of galaxies, quasars, and gas clouds spanning roughly 3.3 billion light-years, located about 9.2 billion light-years from Earth. If the Giant Arc is a real physical structure rather than a statistical clustering artifact, and the debate continues, it too exceeds the theoretical size limit for coherent cosmic structures. These repeated anomalies at the largest scale suggest that our picture of how the universe organizes itself at its greatest extents may still be incomplete. Understanding what drives this organization requires grappling with 2 components of the cosmos that we can detect only indirectly: dark matter and dark energy. Dark matter does not emit, absorb, or scatter light. It interacts with ordinary matter only through gravity, but its gravitational effects are unmistakable. Without it, galaxies would not hold together. Their stars rotate too fast for the visible matter alone to keep them bound. Without it, galaxy clusters would fly apart. Without it, the filaments of the cosmic web could not have formed in the time available since the Big Bang. Dark matter is the scaffolding.
ordinary matter, stars, gas, planets, people, falls into the gravitational wells that dark matter creates, cools, condenses, and lights up.
The cosmic web we observe in galaxies traces a pre-existing structure built primarily from the invisible majority of matter. Dark energy is different in character. Where dark matter pulls, dark energy pushes, or rather, it drives the accelerating expansion of space. Discovered in 1998 through observations of distant supernovae, dark energy appears to account for about 68% of the total energy content of the universe. Its nature is unknown. It might be a property of space itself, an energy inherent to the vacuum, predicted by quantum field theory, though wildly discrepant in magnitude from naive theoretical estimates. It might be a field that evolves over time. It might be something for which we have no adequate theoretical framework at all. Some researchers have proposed an alternative, that dark energy does not exist as a physical entity, and that the apparent acceleration of expansion is an artifact of our position in the universe. If the local group sits near the center of a very large void, and there is some evidence that it does, occupying a region somewhat underdense relative to the cosmic average, then the locally measured expansion rate would appear faster than the true global rate. The non-uniform distribution of matter on large scales would mimic the effect of dark energy without requiring dark energy to exist. This alternative remains controversial, but the very fact that it can be seriously entertained reflects how much uncertainty remains in our understanding of the universe's largest scales. In the heart of all this dark matter scaffolding and dark energy expansion, individual stars continue to be born and die, indifferent to the grandeur of the structures they inhabit. Most stars are small by cosmic standards. The Sun is a middleweight, not massive enough to explode as a supernova at the end of its life, not so small that it will burn for trillions of years. But the universe produces objects far beyond the Sun's scale. Among the most extreme are the red hypergiants. Stars so enormous that they sit at the very edge of what physics allows before gravity becomes catastrophic. One such star was catalogued in the late 1980s as Stephenson 2018, also known by the designation RSGC 2018, a member of the red supergiant cluster Stephenson 2, located in the constellation Scutum, about 20,000 light-years from Earth. For a long time, this star attracted little attention. It sits behind significant interstellar dust, making it essentially invisible in ordinary light. Only infrared observations revealed its true nature. Stephenson 2018 is, by current measurements, the largest known star in the universe. Its radius is approximately 2,150 times the radius of the Sun. To put that in perspective, if Stephenson 218 were placed at the center of our solar system, its surface would extend beyond the orbit of Saturn. The volume it contains is large enough to hold roughly 10 billion suns. Were a person somehow able to stand on its surface? Setting aside the fact that it has no surface in any conventional sense, being a vast cloud of plasma, and travel at the speed of a commercial aircraft, the journey around its circumference would take several thousand years. Stars this large are hypergiants, a category that includes objects with masses far exceeding the Sun's luminosities that can reach several 100,000 times the solar output, and lifespans measured in mere millions of years rather than billions. Stephenson 218 belongs to the red hypergiant subtype, a star that has left the main sequence, exhausted the hydrogen in its core, expanded to extreme radius, and now burns helium in its core while continuing to fuse hydrogen in a shell surrounding it. The precise mass of Stephenson 218 is difficult to determine, partly because it is obscured and partly because stars this large shed mass continuously through powerful stellar winds. Estimates place it somewhere in the range of 12 to 16 solar masses. Large, but in fact not the most massive star known. The record for sheer mass belongs to R136A1 in the Large Magellanic Cloud, at approximately 265 solar masses.
But mass and size are not the same thing. A very massive star can be compact. A somewhat less massive star in a later evolutionary stage expands dramatically in radius.
What awaits Stephenson 2-18 at the end of its life is a core collapse supernova. When the nuclear fuel in its core is finally exhausted, the outward pressure that has balanced gravity for millions of years will vanish in a fraction of a second. The core will collapse, the outer layers will rebound in an explosion of almost unimaginable violence, and for a brief period the dying star will outshine entire galaxies. What remains afterward may be a neutron star, an object the size of a city, containing more mass than the Sun, made almost entirely of neutrons packed together. Or, if the collapsing core is massive enough, it may form a new black hole, and the cycle that connects stellar death to space-time geometry will have completed another iteration. This star, 20,000 light years away, too faint and too obscure to see without specialized instruments, is nonetheless one of the most remarkable physical objects our universe has produced. It is a reminder that even within a single galaxy, the range of objects is almost as astonishing as the range across galaxies. Return now to the void, not a metaphor. A place. In 1981, a team of astronomers, led by Robert Kirshner, was conducting a survey of galaxy redshifts in the direction of the constellation Boötes. Their expectation was broadly typical: galaxies distributed in the rough clumping patterns that had been established by then. What they found instead was a hole, a region approximately 330 million light-years in diameter, containing almost no galaxies at all, in a volume where standard models predicted something on the order of 10,000 galaxies. They found just a handful. Early counts gave fewer than 10, and decades of subsequent observation have raised that number to around 60. The void, as it came to be known, remains one of the largest known voids in the observable universe. Its distance from us is approximately 700 million light-years. To travel across it at the speed of light would take 330 million years. In that entire volume, the density of galaxies is less than 1% of the cosmic average. If our Milky Way resided at the center of the Boötes void, the nearest galaxies would be so remote that human civilization would have had to develop radio astronomy more than 60 years ago before discovering that other galaxies exist at all. The night sky viewed from inside the Boötes void would be noticeably darker. The nearest clusters would appear as faint smears, not the familiar scatter of resolved objects visible from our position. The few galaxies that do inhabit the Boötes void tend to occur along the void's edges and interior filaments, thread-like structures left over from the original boundary regions between smaller voids that may have merged to produce this one. This is one of the leading hypotheses for how the Boötes void formed, not as a single original structure, but as the result of multiple smaller voids coalescing over billions of years, the way soap bubbles merge into larger bubbles. Each merger would have pushed galaxies toward the growing boundary, leaving the interior increasingly empty. The tubular and filamentary shapes of the galaxies found inside the Boötes void are consistent with this model. They look like the remnants of former walls between smaller regions. Inside the void itself, the conditions are as close to perfect emptiness as the universe achieves. The density of ordinary matter is so low that particles rarely interact. A neutrino traversing the void from one side to the other would emerge hundreds of millions of years later in essentially the same state in which it entered. The same applies, somewhat differently, to photons. The void's interior represents the nearest thing our universe has to a pristine vacuum, a region where the history encoded in matter is minimally scrambled by collisions and interactions, where the primordial conditions of the early universe are, in a sense, preserved in the absence of complexity. For cosmologists, voids like this one are not merely curiosities, they are probes. The rate at which voids grow or fail to grow depends sensitively on the balance between gravity and dark energy. A universe with more dark energy expands its voids faster, pushing matter more aggressively toward the surrounding filaments and walls. Measuring the shapes, sizes, and internal structure of voids across cosmic history is therefore one of the more powerful tests of dark energy models available to us. The Bootes void and the several hundred other significant voids catalogued in recent years are data points in an ongoing measurement of the universe's energy budget. They are also unavoidably a reminder of scale. We spend a great deal of time in both science and culture contemplating what exists, galaxies, stars, planets, life. We spend considerably less time contemplating what does not exist and why. The Bootes void contains the absence of roughly 10,000 galaxies. Each of those absent galaxies would have contained hundreds of billions of stars. Each star might have had planets. The void is not an empty stretch of space waiting to be filled. It is a scar of the gravitational history of the universe, a place where the cosmic web's architecture has drawn matter away and left behind silence on a scale that language barely captures. This is the universe as it is, not a smooth, featureless expanse, but a structure, a web of filaments and walls enclosing vast emptinesses, punctuated by dense clusters of galaxies, each galaxy a collection of hundreds of billions of stars, some of those stars large enough to contain billions of suns, all of it embedded in a fabric of space whose shape we are still measuring and whose composition, dark matter, dark energy, ordinary matter we understand at best partially. We look outward from a small planet, around a middleweight star, in an unremarkable arm of an unremarkable galaxy, in a supercluster being pulled toward a concentration of matter we could not even see until recently, in an observable universe that extends 46 billion light years in every direction, which is itself only a portion of a universe that may be vastly, perhaps infinitely larger than what we can detect. And we keep measuring. We build larger telescopes. We launch satellites sensitive to the faintest traces of ancient light. We map the positions of millions of galaxies and calculate the peculiar velocities that reveal the gravitational forces acting on them. We analyze the polarization of photons that last scattered off matter nearly 14 billion years ago. Every new survey adds data. Every new survey also reliably adds questions. The shape of the universe remains uncertain. The nature of dark matter is unknown. The source of dark energy is unknown. The origin of the largest structures, walls that exceed theoretical size limits, rings of gamma-ray bursts spanning 5 billion light-years is unknown. The Eridanus supervoid has no agreed-upon explanation. The filament near Sagittarius A star has no confirmed origin. The Bootes void's formation is modeled but not fully understood. This is not failure. This is the actual state of knowledge about the cosmos. Science advances not by achieving certainty, but by replacing larger uncertainties with smaller, better defined ones. Each answered question reveals the precise shape of the next question waiting behind it. A ship disappears over the horizon, hull first. A curious mind notices the order of disappearance. The world turns out to be a sphere. Then a larger question: what shape is the space in which this sphere moves? And then, what shape is the space in which the space moves? And then, what pulls everything toward the south? And what pulls that? And what lies between the pulling? The questions extend outward in every direction, into the same darkness that has always been there, waiting.